Now for the next oral communication, we have Gabriel Ribeiro, who is going to talk to us about singular spacetime with bounded algebraic curvature scalars.
Good afternoon, everyone. So my name is Gabriel Ribeiro, and today I'm going to talk about singular spacetimes with bounded algebraic curvature scalars, which is based upon a work of similar title done in collaboration with Renan, Haroldo, Professor Gonzalo, and Professor Crispino. So this presentation is roughly divided in two parts. A primer on singularities, in which I will briefly talk about the concepts that we've made use in the work, and the setup in which I applied those concepts, and finally the conclusions. So everyone firstly learns about singularities in GR by solving the Einstein's field equation in the vacuum using a spherically static and spherically symmetric NZ. So the solution, as we all know, is the Schwarzschild solution, which a priori it's problematic at the origin and at r equals 2gm. But we learned that this r equals 2gm region is not really problematic in a physical sense, since a change of coordinate can solve it. So we make use of curvature invariants to help us understand the real problematic points in a given spacetime. For instance, one can calculate the Kretschmann scalar, and one sees that it is regular at the r equals 2gm point, but it is unbounded at the origin. So the origin is indeed the problematic point. So this raises a question. A divergent curvature scalar implies in a singularity, but the presence of a singularity implies in the presence of a divergent curvature scalar. So it turns out that the presence of divergent curvature scalar is not really good for defining what a singularity is. And the best and most widely accepted way of defining a singularity is by by the presence of incomplete paths in a given spacetime. So an incomplete path is a path that cannot be extended through a point, right? Or it cannot be, if you trace back the trajectory, it cannot be indefinitely traced back. So this means that an observer reaches the boundary of the space in a finite proper time. Although this is a nice way of defining it, it says nothing about the nature of the singularity, in the sense that it says nothing about what happens to physical bodies approaching the singularity. So for us to understand what happens to physical bodies nearby singularities, we have to study what we call Jacobi fields. So the Jacobi fields are governed by this equation, which is the Jacobi equation, and with three linearly independent Jacobi fields, one can define a volume form, and this volume form tells us about the evolution of extensive bodies, and it can tell a great deal for us about how physical bodies behave nearby singularities. So with this, we can start by classifying space-time singularities by their impact on observers. So usually strong curvature singularity occurs when an object is infinitely compressed to a zero volume, and the necessary condition for the occurrence of such a singularity is given by the divergence of this integral. But a sufficient condition involves other things, such as involves the no convergence condition. So there is some broader ways of defining singularity strength, which is known as deformationally strong singularities. So our setup is basically study some asymptotic internal region of solutions that arises from two different models of gravity. The first one is the Palatini-Ibit theory, coupled to some canonical scalar Lagrangian, and the second model is the quadratic Palatini gravity, coupled to some nonlinear scalar field. So both those solutions present the same geometric geometric structure in the asymptotic internal region, which is encompassed by this boxed line element. So the parameters alpha and beta are defined by the theories, and one can calculate invariance, curvature invariance by in this case, and see that they are all bounded in the asymptotic internal region. So it raises a question: when does one stop calculating curvature invariance? It turns out that there is, in some sense, some complete sets of curvature independent curvature invariance, and one such complete set is the Zachary-McIntosh set, and it is formed by 17 invariants, and all of them are bounded in the asymptotic internal region. So we have to understand what happens to paths in this space-time. So we investigate radial geodesics in this case, which is for massless particles is the first bullet point, and for massive particles is the second bullet point. And for the massless case, one sees that at a finite affine parameter value, the particle approaches the asymptotic region. And for the massive case, the same thing happens. So the space-time is geodesically incomplete. Now, to understand what happens to physical extensive bodies, we have to understand what happens to the Jacobi fields of objects following those incomplete paths. So we chose a tetrad basis, and we calculate the parallelly propagated components of the Riemann tensor, and one sees that the angular components of this parallelly propagated components of the Riemann tensor is unbounded at the asymptotic internal region. So this points to a parallelly propagated curvature singularity, and furthermore, although the necessary condition is fulfilled, the sufficient condition isn't. So what's left to us to investigate is if this singularity is deformationally strong. So we start by writing the line element using no coordinates, and using some ansatz for the Jacobi fields and some initial conditions. We find that the volume of the volume for the volume zero for approaching the singularity is unbounded. So it is indeed a deformationally strong curvature, deformationally strong singularity. So we conclude with this, that curvature scalars are insufficient to point out the pathological nature of space-time, and path completeness is better suited for this. And we conclude also that not being a strong singularity does not imply in the non-destruction of observers, since the study of individual Jacobi fields is better suited for this. Thanks, everyone.
Thank you, Gabriel. Any question or comment? If you have no comments, let's thank Gabriel again.